Hi, welcome to Algebra 2, Lesson 3-6, Theorems about roots of polynomial equations. In this lesson, we'll be able to use roots of a polynomial equation to find other roots. So let's start with critique and explain. Look at the polynomial function shown. G of x is equal to x squared minus 7x minus 18, and h of x is equal to 5x squared plus 24x plus 16. So looking at the two polynomial equations, we should think about these questions here. So Avery has a conjecture that the zeros of a polynomial function have to be positive or negative factors of its constant term. Factor g of x completely. Are the zeros of g factors of negative 18? So first of all, let's factor g of x completely. And so that's equal to, think about the factors of negative 18. We have 9 and 2, but one has to be negative. So we know it's going to be negative 9. So that we have, in addition, a sum of negative 7. So x minus 9 times x plus 2 would have a multiple of 18 and a sum of negative 7 here. Are the zeros of g factors of negative 18? So from the factors, we know that the zeros are 9 and negative 2. And they're both factors of negative 2 as well. So yes, they are both the factors of negative 18. So let's first write the factored form. G of x could also be written as x minus 9 times x plus 2. And answer the last question. 9 and negative 2 are both factors of negative 18. Okay. Part B. Now test Avery's conjecture by factoring h of x. Does Avery's conjecture hold? If so, explain why. If not, make a new conjecture. So, what's her conjecture? The zeros of the polynomial function have to be positive or negative factors of its constant term. So it has to be a factor of the constant term. So let's factor h of x. If we factor h of x, remember we have the coefficient 5, the leading coefficient 5. So one has to be 5x, and another would be just regular x. And then this term, this constant term, would be equal to, would be multiplied to 5, and then would have to add up to 24 with this factor, right? So factors of 16, we have 16 and 1, 2 and 8, 4 and 4. So 4 times 4 is 16, and it's positive 16. 4 plus 4 is 8, but if we multiply 4 times 5 is 20. So 20 plus 4 is 24. So we know that it's going to be plus 4 on both sides. There we go. So we can rewrite h of x as these two factors. H of x is equal to x plus 4 times 5x plus 4. And what are the zeros? So looking at the first one, when 5x plus 4 is equal to 0, then 5x is equal to negative 4, and x is equal to negative 4 over 5, but square root of that, wait, no, that's negative 4 over 5. And then x is equal to -4 for the other root. And so are these factors of 16? No, if you multiply them, it's 16 divided by 5, not 16. So it is not, but is it related to 16? Yeah, you divide it by 5. So what's a new conjecture that you can make? So it's still going to be a factor if you divide it by the leading coefficient. 5 comes from the leading coefficient, right? So yeah, that would be a conjecture that would work. Good. So let's put that into words. So no, the zeros of a polynomial function are a factor of the last coefficient divided by a factor of the first coefficient. Okay, good. So the essential question for this lesson would be, how are the roots of a polynomial equation related to the coefficients and degree of the polynomial? So keep thinking about the relationship between the roots of the polynomial equation and the coefficients and the degree, the key features of the polynomials. So let's first look at this concept of the rational root theorem. So I'm just going to state the theorem first and then explain. Let P of x equal a sub n times x to the nth power plus a sub n minus 1 times x to the nth power plus dot 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 with the same pattern until a sub 1 times x plus a sub 0 to be a polynomial with integer coefficients. Does this look familiar? Yeah, we looked at the Pascal's triangle, right? It looks like the it looks like the theorem that we looked at beforehand, right? So the polynomial equation P of x is equal to 0 has any rational roots. Then each rational root is of the form P over Q, where P is a factor of the constant term a sub 0, and Q is a factor of the leading coefficient a sub n, which is what we just figured out from critique and explain. So there we go. I don't need to explain further because we already looked at how we got to this conclusion from critique and explain. And that is why this is a great introductory question, because yeah, before we even looked at the concept of rational root theorem, we figured it out by ourselves. So now you understand. But by words, you can state the theorem like this. Example 1, identify possible rational solutions. From the graph, it appears that 4 is a 0 of the function p of x is equal to 8x to the 5th power minus 32x to the 4th power plus x squared minus 4. So yeah, it is true because there's a 0 here. It passes through the x-axis here. Without substituting, how can you determine if 4 is a possible solution to p of x is equal to 0? By graph, you can see that it is a possible solution. But if we look at the theorem and make connection with that, we can use the theorem to figure out the factors of the coefficient, the constant term, and divided by constant term, p of q, p over q, right? So q is here, -4. Wait, that's p. So p over q, we need to see p over q. So -4 divided by 8. Right? But we need to figure out the factors of p and the factors of q. So -4 is a factor of -4, right? 8 is a factor of 8, but there are other combinations as well. So -2 is a factor of -4, and then +4 maybe is a factor of 8, and so on. So there are many factors of 4 and 8, including the positives and negatives, right? So there are many combinations of these factors. So all the possible rational roots of p of x here are these: plus and minus 1, plus and minus 1 over 2, plus and minus 1 over 4, 1 over 8, 2 over 1, 2 over 2, which is 1, 2 over 4, 2 over 8, 4 over 1, 4 over 2, 4 over 4, 4 over 8. There are some repeated numbers because we're listing all the different combinations of these two factors, but factors of p and q. But if you look at it, 2 over 2 is the same as 1 over 1, right? They're basically same number. But so we can cancel out some of the repeated ones, and then we can see, oh, there are a few possible things, and you can try to figure it out. But but if you notice, 4, which is 4 over 1, is positive 4 is one of the possible values. So it is possible, right, to have it as a 0. So using the rational roots theorem, you can also back up your explanation, your claim. Okay. These are possible roots. It doesn't mean they are actual roots. So from here, you'll be able to see if it's actual or not by graphing or by using algebra. But this is just another way to say, oh, these are possible roots. So it's not weird to have 4 as a, maybe, in the graph it looks like 4, but actually maybe it's 4.1, right? So when things like that happen, you can double check your solutions when you're looking at the graph by the possible factors, and that's how this theorem is useful. Okay, let's look at try number 1. List all the possible rational solutions for each equation. So looking at the theorem, rational roots theorem, use it to list all the possible rational solutions for the equations. Pause the video and come back when you're ready to check your answers. Okay, are you ready? Okay, so for A, you are looking at -8 and 4. And the factors of -8 comes on the top as a numerator. And the factors of 4 goes in the bottom of the fraction and in the denominator. So list all the possible solutions. Maybe I should write it not. Yeah, so for part A, you will have plus or minus 1 over 1. Let's start from the smallest ones, right? 1 times 8 and 1 times 4. And then plus or minus 1 over 2, the factors of 4, plus or minus 1 over 4, right? The factors of 4. And then move on to the next factor of 8, plus or minus 2. Over 1, and then plus or minus 2 over 4, and then plus or minus 4 over 1, and then plus or minus 4 over 2, and then plus or minus 4 over 4, and then plus or minus 8 over 1, and then plus or minus 8 over 2, and plus or minus 8 over 4. Okay, good. And I think that's all. Yeah. What about part B? You're looking at the constant term, -45 and 7. So the factors of -45 go on top. Factors of 7 go on the bottom. So we have more possible solutions than A. So starting with 1, we have plus or minus 1 over 1, plus or minus 1 over 7. So as you notice, plus or minus 1 over 1 could be possible factors of any two combinations of numbers, right? Real numbers. So when you're checking for possible solutions, when you don't have enough information, maybe you can check 1 first or -1 first, and that's a really good way, good start when you have to guess and check. Okay. Well, anyway, let's continue on. We have plus or minus 3 over 1. We have plus or minus 3 over 7. We have plus or minus 5 over 1. We have plus or minus 5 over 7. And then we have plus or minus 9 over 1. We have plus or minus 9 over 7. It's good that we only have 2 possible factors for 7. We're going faster than I thought. So we have plus or minus 15 over 1, and then we have plus or minus 15 over 7. We have lastly plus or minus 45 over 1 and plus or minus 45 over 7. Okay, good. Are you checking your answers? So check your answers and see if you got everything. And if you did, great job. These are all possible rational solutions using the rational roots theorem. We'll continue with the next examples in the next video.